Hi again, everyone. I hope you've all had a wonderful time learning about the inspiring and impressive research across both campuses. Can I ask everyone to once again thank our presenters for sharing their work this afternoon? It is with great honor and anticipation that we welcome Professor Phillip Milner to deliver today's keynote address. Professor Milner is an associate professor at Cornell University in the Department of Chemistry and Chemical Biology and is a member of the Cornell Energy Systems Institute and the Cornell Center for Materials Research. His work resides at the intersection of synthetic organic chemistry and materials chemistry, with a focus on grappling with translational issues in carbon capture, energy management, and medicinal chemistry. Dr. Milner has been recognized numerous times for his expertise in research, most recently at ACS this year, where he was awarded the ACS Award in Pure Chemistry. So without further ado, please join me in extending a warm welcome to Professor Phillip Milner as we eagerly await his insights into taming the halogens using metal organic frameworks.
Thank you all for coming. I don't know what possessed you to come to a chemistry talk on a Saturday afternoon, but I really appreciate you all for being here. And I hope you had fun at the poster session, especially on behalf of the local ACS section, of which I'm the chair. We're excited to have a really good turnout here, and it seems like a lot of good scientific discussions were had, so excellent. And now you have to suffer through my talk. All right, so I'm going to tell you about some of the work that my lab does at the intersection of doing synthetic organic chemistry, but using metal organic frameworks, which are materials probably most of you now are familiar with because they just received the Nobel Prize last fall. And I did not get the Nobel Prize. But I can tell you about the way that we try to use these materials in a new and interesting way. And so, like I said, our group is interested in this kind of intersection between material science and organic synthesis, where we try to design materials to tackle longstanding challenges in organic chemistry, specifically the synthesis of drugs and drug-like molecules, and also taking advantage of our insights as organic chemists to design better materials, which I'm not really going to talk about too much today because of time. And so if I try to distill down our group's research into one slide, what inspires us, it all comes back to the dual nature of my favorite element on the periodic table, fluorine. And so fluorine is incredibly important in many different industries. Up here, I'm just highlighting its importance to medicinal chemistry. The number of FDA-approved fluorinated drugs you can see is just increasing and increasing every year. It's in about a third of all FDA-approved drugs. It's also in an even higher percentage of agrochemicals and polymers and biomedical imaging agents. Fluorine is everywhere in medicine and the agricultural industry. But fluorine also has this dark side. And some of you may be familiar, for example, with PFAS that is kind of really dominating the news right now. Those are the kind of one of the problems with fluorine, these forever chemicals. Another that's not as well known is that fluorinated gases are some of the most potent known greenhouse gases. So for example, the most potent greenhouse gas known is sulfur hexafluoride, which has a global warming potential. It's about 25,000 times greater than that of CO2. So each molecule is equal to 25,000 molecules of CO2. Of course, CO2 is still a bigger problem because we emit much more, but each end of those fluorinated gases are particularly problematic. And you can see there's a huge range of them that are used across the refrigeration and semiconductor manufacturing and also chemical manufacturing. So when we think about designing materials, I didn't mention this here, what we want to think about is how can we design materials to make fluorinated chemicals? And on this side, we want to think about if we have mixtures that contain fluorinated chemicals, how can we selectively remove them and trap them and potentially turn them into drug molecules? So our kind of big picture dream would be, can we capture fluorinated greenhouse gases at their industrial point sources and turn them around and make them into something valuable, pharmaceuticals, for example, that could save lives? Okay, and that leads our group to have a lot of diverse interests involving metal organic frameworks. But I'm going to start off by telling you a little bit about how we think about making these types of metal organic frameworks and what their structures are. So metal organic frameworks conceptually are actually quite simple. They're really just polymers where you take an organic component here that has multiple binding groups to bind to metals on it. We call that the linker. And we take these symmetrical inorganic building blocks that we call the nodes. And so the linkers will coordinate to the nodes. You will basically polymerize in solution, but that reaction is reversible. The coordination is dynamic. That allows us to correct errors as the material forms, eventually forming this infinite structure that precipitates out that we call the Metal Organic Framework, or MOF. And why we and many others are excited about these materials and what led them to receive the Nobel Prize last year is that they have these holes in the structure here, these pores that guests can diffuse into. They can be gases, substrates, catalysts, proteins, whatever you can think of. You can design a material where you can bind it and control its local environment in a way that's very difficult to replicate in solution. And we think they have a lot of potential advantages for organic chemistry in particular. That long range order you get from that error correction means that they are what's called crystalline. So they have the same structure repeating over and over. That means we can control that structure, we can understand it, we can model it computationally very easily. Another nice thing about MOFs is they are insoluble in all organic solvents. So we can kind of do guilt-free catalysis where we can recover these materials when we're done with them, reuse them, recycle them many, many times. And we can also control and install active sites that are really unusual, hard to make in solution. I'll show you some examples of that today from our group. One of the big questions when we started was, how do you make metal organic frameworks? So actually, it's usually relatively simple. You take some metal salt and some organic thing and you mix them together, you boil them in solvent, and the MOF precipitates out. And your workup is filtered, which is nice. There's no columns or anything. But some MOFs can still be quite difficult to make, even if you want to make like a gram of it to test out as a new catalyst or reagent. So we've developed a number of really user-friendly ways to make these materials. So for example, Tyler, a graduate student in our lab, found that you can actually many times just melt the organic linker and a metal salt together. And the MOF will form in the molten metal salts as the solvent and the precursor to make the material. Now this works well when it works, but it is a pretty harsh synthesis, pretty high temperatures. It generates HCl as a byproduct. So we had to come up with other ways to make more delicate frameworks. So for example, Ron in our lab found that another way to make MOFs, we can use just a little bit of solvent. Usually MOFs are made in a very, very dilute condition, something like 0.01 molar, really slow, like we're doing a crystallization. And so we found we can actually run them at concentrations more like a typical synthetic procedure, and they work just fine. And that works for many, many different types of MOFs. So along the way, we had some fun discoveries with that. So for example, Tristan, another graduate student, Arjun, a postdoc in our lab, found that sometimes when you try to do that, the wrong MOF forms. And so you try to increase the concentration. For example, when we were trying to make this material here, which we'll talk about a lot today in just a bit, we got these other structures instead, just by changing the concentration. So that's something you have to watch out for when doing this. And actually a team of undergraduates in our lab, Tony and Elena, along with graduate student Ruth, were able to solve that problem to some degree by adding some base and grinding everything together here in a ball mill. You can just grind all the precursors together and make MOFs. And if you put this all together, thinking about making MOFs at high concentrations, adding base, grinding, stirring very aggressively, you can come up with actually a pretty general way to make MOFs in water as the solvent. So this was pioneered by a graduate student, Caitlin, and then followed up by an undergrad, Zaim, who just graduated. They were able to show that this is a pretty general way you can make MOFs in water. And I think Caitlin put all the MOF that she made in all these vials instead of a jar because it looks really impressive to have 30 vials of MOF you made. It's very impractical though. So that's kind of gives you a little bit about how we make MOFs. And what I want to talk about now is what we can use them for to develop new synthetic transformations that will be useful, particularly for medicinal chemistry. And so what I'm going to start off by thinking about them is how do we make MOFs function as catalysts, as molecules or materials in this case, where we can use them to mediate a transformation that's otherwise quite difficult to do directly. And there's a couple of features we need to keep in mind. If you think back to that image of MOFs I showed you, they have these pores. We need to make sure those pores are big enough that our substrates can all fit into the material. We want to try to install reactive sites, and in particular in our lab, we try not to just mimic what we can do in solution already, but we want to install an active site that you can't mimic very well in solution. And of course, we always want to prove these materials are recyclable, survive the reaction, we can use them over and over again to make this really sustainable transformations. And so when we think about what are the reactions we need catalysts for, people develop catalysts all over the world. And our motivation has been to think about what are the most widely conducted reactions in drug development. Pharmaceutical synthesis is actually incredibly unsustainable, particularly fluorination. So all fluorine, for example, comes from one mineral, fluorspar. which has to be ultra high purity. It's really only found more or less in China, and there's only less than 100 years of it left. And so fluorination is really unsustainable, but pharmaceutical synthesis in general is really, really, really wasteful. So for example, if we look here, this is a list of some of the most important reactions in pharmaceutical industry by one metric, which is the percent they appear in medicinal chemistry journals. And you can see these are pretty simple reactions. Probably most of you have learned these before: amide coupling, deprotections, hydrolysis. What I think is most remarkable about this plot is only one of these reactions is typically done catalytically, which is the Suzuki-Muir coupling. The rest of these are done stoichiometrically, generating significant waste. This is most of the waste of the pharmaceutical industry right here. And so we wanted to design heterogeneous catalysts. We have made catalysts for amide coupling. I'm not going to talk about that today. I'm actually going to focus on the second most widely used reaction in pharmaceutical industry, which is nucleophilic aromatic substitution. And this reaction is a reaction where we can exchange halogens on electron-deficient aromatic rings, particularly heteroaromatic, six-membered heteroaromatic rings. And these are just a couple of examples of bioactive molecules that contain halogenated electron-deficient heterocycles. This one I think is really cool. This is the poison of poison dart frogs. Actually, it contains that functional group. And why we were interested in this is the way we make these is typically with very, very harsh nucleophilic aromatic substitution. If you've learned about that reaction, you know it typically requires high temperatures. So here we are driving these reactions at 230 or 250 C to exchange these chlorines for fluorines in these molecules. And if you think about why that is, it has to do with the reagent right here. We're using something like potassium fluoride to do this reaction. And in potassium fluoride, this is the structure of potassium fluoride. Those gray atoms are the potassiums. Those are the fluorides. They're buried in the lattice. So this is not a very reactive fluoride source. So we have to use really high temperatures, agents to dissolve the fluoride source, things like that. And so we thought maybe what we need is what we call a naked halide, or a halide that's not buried in a lattice like this, but is actually exposed in the pores. And we thought we could do that in MOFs using particularly this cobalt-based MOF that had been reported previously. So this is the linker here. The node of it is actually an infinite node. It is metal halide chains. And so this MOF has relatively large pores. The structure of it looks actually like a honeycomb. So it's hexagons in the screen, and then one-dimensional channels going into the screen here. This is the structure. And the reason why we thought this was good is this MOF, it was known that you could actually, it has cobalt-2 sites to start with, but you can actually oxidize it up to cobalt-3. And when you do that, you need a charge balancing anion, right? You oxidize the cobalt, you need an anion. And that anion actually points right into the pore. So we thought this might actually be a naked halide anion. So the first thing Tyler, a graduate student in our lab, did was he showed that you could generalize this to make any type of halogenated MOF through down the halogen series, fluorine, chlorine, bromine, and iodine. And he also showed that they are labile that can exchange with each other inside of the MOF. And long story short, this MOF is able to catalyze this halogen exchange reaction here. And you can see under much milder conditions, I was showing you 250 C before, now we can do it at only 90 C. And the reaction only works when you have a catalytic amount of the MOF present. But we did some control experiments just to prove that the MOF is definitely the active catalyst in this reaction. So the way it works is you essentially do what looks like a traditional SNAR type reaction here, where you have the halide and you do a halide swap with the aromatic ring on your cobalt. Here gets the other halogen, and you turn it over using the exogenous halide salt like KCl. And so you can actually prove this using a cool technique that's unique to materials called energy dispersive X-ray spectroscopy, or EDX. What it allows you to do is actually map the elements present in your sample. And so, for example, if you look at the starting MOF here, you just see chlorine and cobalt. That's the molecular formula of the MOF, and that's the traditional kind of SEM image of it. So you can see the cobalt and the chlorine. There's no bromine. But when we take the MOF and mix it with an aryl bromide, we get a halogen swap. So chloride goes into the molecule and bromide goes into the MOF, and we can actually now see bromide using this elemental mapping technique. Long story short, this reaction works quite well to do halogen exchange in many different aromatic systems. You always want to show that your reaction can work with a broad scope, and in particular, when you're doing heterocycles, 5-member heterocycles are by far the most important. They are incredibly common in drug molecules compared even to 6-member ring heterocycles. And after a little bit more work, Tyler was also able to extend this to fluorination as well. Here you have to add a solubilizing agents because fluoride salts are so insoluble that you can't really get the turnover of the catalyst. But if you do that, you can actually get fluorination to work as well. And one of the nice things, as I mentioned about MOFs, just to highlight it about their heterogeneity, is that we can do kind of guilt-free chemistry with them. We can use them in what's called continuous flow, where we pack a column with MOF and halide salts and we just flow our substrate through. The product comes out on the other side. Sounds like perfect chemistry, right? It's a really nice, easy way to do it. And it works because the MOF is insoluble, so you can flow the substrate through and it doesn't really dissolve. And we also were able to recover the MOF and recycle it several times here. But thinking about what we could do with this MOF also led us to think about other reactions of metal halide species that could be possible. So I just showed you that a cobalt chloride, a cobalt-3 chloride, could be quite nucleophilic. But we thought that if we could change that metal, we could change the nature of that chlorine and thus change its reactivity. And in particular, Mary, another graduate student in our lab, thought that if you could put copper sites in the MOF instead of cobalt, instead of getting nucleophilic reactivity, we thought we could get radical reactivity by shining light onto this copper MOF through a process called ligand to metal charge transfer, where when you photoexcite this material, the charge goes onto the copper. The other way around. The charge goes onto the copper, and the chlorine ends up being oxidized and comes out as chlorine radical. And probably most of you learn about free radical halogenation. When you make chlorine radical, it can grab CH bonds off of hydrocarbons, and you can do CH activation that way, CH functionalization. And so long story short, this reaction does work. I'll show you the mechanism in just a little bit, but Mary was able to use this copper-based MOF called MIT20 lithium chloride. And by the way, if you're trying to figure out the naming system for MOFs, don't bother, it's a complete mess. This MOF was discovered at MIT. Usually you name it after the school. So for example, MOFs that we discover are called corn MOFs, corn for Cornell. You can use this to actually do CH abstraction from the solvent here, in this case, tetrahydrofuran, and trap it with an alkene, like radicals love to add to alkenes. And I'll just summarize by saying that Mary did a lot of control experiments just to show that the MOF is definitely the active catalyst here. There's no solubilized copper species or anything like that going on. And you need light for the reaction too. So this reaction works well with a broad range of different alkenes, including this crazy one, which is made from 2 molecules of cholesterol attached onto the alkene. Mary accidentally crystallized that. Actually, you got a crystal structure that was completely useless, but it's kind of cool. It's a very long molecule. But what's really interesting to us is if you look at the scope of the partners you're abstracting the CH bond from. Because while it works for ethers, which are kind of classic substrates, the CH bond next to oxygen is quite weak. For example, in all these ethers. It also works for amines, same deal. But most interesting to us was that it also worked for alcohols. That CH bond is quite weak, but typically a problem with alcohol substrates is you get overoxidation. So for example, if you use molecular copper salts and shine light on them in the same way, you get a lot of ketone formation instead of the functionalization of the alcohol. Once you abstract a CH bond, it's so easy to just remove the other H from the O and make the ketone. That's a great thermodynamic driving force. And so that told us that the MOF is different than just molecular copper chlorine. And so Mary did a lot of experiments to try to understand why. One of those was something probably most of you learned about, a kinetic isotope effect study that allows you to see whether CH bond breaking is part of the rate limiting step or occurs before the rate limiting step in the reaction. And indeed, we see a very strong kinetic isotope effect, which is unusual because free chlorine radical you generate like photolysis of chlorine gas doesn't usually show much of a KIE because chlorine is so angry, it just wants a CH bond. It doesn't really care if it's a deuterium or whatever. And we also did some calculations with our collaborators at MIT who also helped support this, that the photolysis of the copper chlorine bond only really occurs in the presence of substrates. You don't get full release of chlorine radical, you just get a lot of radical character on the chlorine and it can do the CH abstraction. So this is the mechanism of this reaction. You take those copper chloride salts, you shine light on it, and you you extract the CH bond here to make the radical here, which can then add to the alkene partner to give you over here, and then you do one last turnover of the catalyst. Essentially, the copper gets the electron back. The copper gives the electron back, and then you do a protonation, and that gives you the turnover of the catalyst here. And some of you probably saw Sky's poster. It's actually inspired by this work because when doing this reaction, Mary discovered an unusual contra-thermodynamic isomerization of the alkene, which Sky has been following up on here, which I think is very, very cool. A reaction type that hasn't really been seen very well with MOFs. So hopefully Sky did a good job explaining it. I'm sure he did, probably. Okay, so I'm just picking on Sky. Okay, so I want to shift gears here a little bit and tell you about another way we think MOFs could be useful in halogenation chemistry. And so what we're going to think about now is not MOFs as catalysts, but as vessels to deliver reagents. We want to store reagents inside and release them on demand to do hard chemistry. So now what we actually want are really small pores, so our substrate doesn't go into the MOF and get confused. We just want the reagents to come out of the MOF. And our inspiration here was thinking again about fluorination chemistry. I've told you already this is really important, but if you look at the types of fluorinated functional groups, there's an incredible diversity, in particular of fluorinated alkenes, which are really difficult to make actually. And I'll show you some reasons why those are important as we go throughout the talk. But what we noticed is that, for example, if you look at this antiviral compound here, it takes 5 synthetic steps to basically install this really simple looking functional group here. And so we thought we could do better than that, right? We can do this natural disconnection right here and do something where we take this vinyl bromide substrate, combine it with a simple molecule like vinylidene fluoride, and we can make that in one step. Sort of a natural disconnection. The problem is, while vinylidene fluoride, VDF, is very cheap, it's used to make polymers, it's used in battery materials, for example. It's a commodity chemical, but it is a gas. And not only is it a gas, but it's really difficult to work with because it's, and many other types of fluorinated gases, I already mentioned, are very potent greenhouse gases, for example. Many of them are toxic and otherwise hard to work with in the laboratory. So our idea was, can we come up with a general approach to facilitate reaction discovery using these difficult to work with fluorinated building blocks? We can start to build towards that goal of turning greenhouse gases into treasure. So if you want to do reaction development with gases, it can be as simple or as difficult as you want it to be, but what it generally is very low throughput. If any of you have had to deal with generating a gas or working with one, it can be quite difficult to do. Our idea was to take advantage of the pores in these MOFs to absorb gases. They are really good at absorbing gases. That's one of the things that led to the Nobel Prize. But now use them as reagents so we can handle essentially solids as gases. Sorry, handle gases as solids. Doesn't really work the other way around. So we can handle gases as solids here where we can actually absorb the gas, we can do our reaction. And the cool thing is we can recover the MOF and reuse it. And this allows us potentially to do high throughput reaction discovery with gaseous molecules. So the first thing we had to do was figure out what's the best MOF. There are actually tens of thousands, probably 20,000 MOFs at this point, where you could combine different inorganic nodes and organic linkers. So we had no idea where to start because no one had ever looked at this before. So graduate student Mary Zick started there by measuring fluorinated gas binding in a range of different porous materials, not just MOFs, but also their fully inorganic cousins, which are called zeolites, or like molecular sieves, if you've worked with those before. And what she found was this magnesium-based MOF, the one that I showed in lots of vials a little while ago, was the best in terms of the binding enthalpy, so how strongly it binds, and the binding capacity, how much gas is absorbed in the material. And I think what is a little bit trippy here for students sometimes to think about with gas absorption is you're essentially moving a gas from the gas phase into the solid phase. It comes with a remarkable decrease in volume. So almost a 200-fold decrease in volume when you absorb a huge atmosphere of gas into a solid. And actually the thing that I think really trips people up is if you think about what this means, is if you take a cylinder that you pressurize with gas, it holds a certain amount of moles of gas, right? If you first take that cylinder and load it up with MOF and then pressurize it, it actually holds more gas, even though it's filled with solid, because it has so much surface area for the gas to bind to. Why this MOF is so good, we can figure out from looking at the structure. It has, again, the same kind of honeycomb lattice that I showed you before. But at the corners of those hexagons are these magnesium sites that have 5 ligands holding onto the magnesium, holding them off together, and a 6th that doesn't have anything on it. And that makes it incredibly Lewis acidic. And so gases like vinylidene fluoride, so that's VDF right there, like to come in and bind through a Lewis acid Lewis base interaction. And what's cool is what we found is that's actually pretty general. Many different fluorinated gases like to come in and bind to that same magnesium site, making this a pretty general approach to binding gases inside of MOFs. So when we started making these, we were doing this in a very proper way. I just want to walk you through how you make these. This is the moth, by the way, if you're thinking this is some cool gemstones or something, it's just this powder. But that powder, when we dose it with gas, is 30% gas by weight, even though it looks just like a normal solid. So we can dose it here using the cylinder into the moth, but we can actually do it with a balloon. This is pretty cool. You can actually fill a balloon with gas and stick it in the moth, and the moth will absorb all of the gas out of the balloon and will deflate. And you can also generate the gas and trap it as well. That was shown by a postdoc in our lab, Chen. And so again, we can take these gas-loaded moths, we can take them as their native form or load them into little wax capsules and drop them into solution. And what we see is when you do that, all the gas basically comes out really quickly. Unless it's in that little wax capsule, then you can imagine the moth has the gas that's inside wax. It just chills in the solvent. Until you sonicate it, you break the capsule, solid comes out, and then the gas comes out, and you can actually set up many different reactions and just sonicate them, and now they're saturated with gas. So let's take a look at what types of reactions we have been able to discover using this approach. And I'll try to go through this quickly so I don't go over too much on time. Also, it's Saturday afternoon. I know that. Even though what every professor loves more than anything is to listen to themselves talk. So we were really interested in these fluorinated alkenes because they are actually what are called bioisosteres for amide. So bioisostere means a functional group that you can replace another functional group, and it has very similar biological activity, but so it has kind of like the same size and shape and polarity, but it's much more stable. That's usually what you want in a good bioisostere. And vinyl fluorides are bioisosteres for the most common functional group in bioactive molecules, which is an amide. So for example, you can take an amide here. If you squint your eyes, this vinyl fluoride here looks a lot like the amide in terms of dipole, but it is much more stable. We don't have any enzymes that know what to do with that vinyl fluoride, right? We have plenty of enzymes that can cleave amides in our bodies, but not vinyl fluoride. So it's much more stable. But what I really like about this story for this molecule here, luenkephalin, where you take the amide and turn it into vinyl fluoride, it improves all of the biological properties. But what it also does is adds 14 steps to the synthesis, because making vinyl fluorides is hard. So it's not useful for anything. And so that's been our inspiration to think about better ways to make vinyl fluorides. So long story short, Feng and Caitlin, working with an undergraduate, Julia, who also just graduated, were able to discover this reaction here where we can use a palladium catalyst to make vinyl fluorides from boronic acids here. If you look at the substrate scope, you can see a couple of unusual partners for Suzuki coupling. If you've learned about it, usually it works on aryl halides and alkyl halides, but they're tolerated in this reaction. And a lot of mechanistic work showed us why that is. This reaction does not proceed through a normal cross-coupling mechanism. It actually proceeds through what we call an all palladium 2 mechanism, where we do transmetallation, the alkene binds, and then we do this migratory insertion followed by beta fluoride elimination. If you've taken organometallics, you probably know what I'm talking about there. And then last, that gives us our product, and then we get out, we turn over and use transmetallation here. But what this really, the big picture here thing, what I want to talk about is really this step told us that vinylidene fluoride, VDF, is much more electrophilic than had been appreciated in the literature. And that inspired Caitlin to think that it might actually be able to be a good electrophile to react with other types of nucleophiles, not just palladium and boronic acids, but for example, nitrogen heterocycles, which I already mentioned are very common in drug molecules. And so these types of fluorinated N-fluorovinylated or these N-fluorocyclopropanated products are very, very common in drug molecules. They're difficult to make, but there's some interesting biological properties here. And what Caitlin figured out based on that was that vinylidene fluoride is so electrophilic that it can actually just react with nitrogen heterocycles directly. No need for a metal catalyst, just base to grab the proton. And long story short, it works better than any other way you can come up with to do this reaction, to release the gas from the moth. And so this is a bit of an unusual reaction. You might be thinking to yourself, what the heck could be the mechanism of this? It looks like an SN2, but you probably learned you can't do SN2 with either alkyl fluorides or sp2 hybridized carbons, right? So it might be more like an SNAR type reaction, addition elimination. But our DFT calculations at least support that it goes through a concerted mechanism where the nitrogen heterocycle attacks this carbon right here as the fluoride is leaving. And this can happen because you have two fluorines that are pretty inductively withdrawing carbon, so it's quite activated for nucleophilic attack. We also see evidence for that if we add deuterium into the reaction, a huge excess, we don't see any deuterium incorporation, so there's no negative charge likely built up ever on that terminal carbon. This reaction works with basically every type of nitrogen heterocycle you can imagine in your mind, with 1 or 2 nitrogens in it, many different variations. And what I think is cool is it also works on biomolecules. And this shows you kind of the scope of different types of nitrogen heterocycles that are found in drugs. So for example, what I always love this example, look at this, how many functional groups and motifs are in this molecule, and all you do is N-fluorovinylate right there. So it's very selective. So one last story about how we can use these, and I'll talk a little bit about photochemistry and electrochemistry using these. So one more gas that we were interested in is sulfuryl fluoride, SO2F2, because you can use these in drug design to covalently modify proteins using a reaction called SUFEX, which is kind of like a click reaction, if you've learned about the click reaction before. And the problem with this, although, is the best way to make those types of sulfuryl fluoride species, these SO2F warheads, they're called, is using this gas, sulfuryl fluoride or SO2F2. It's very chemoselective, it's very atom economical, it works great. The only problem is it's toxic. It's actually used to kill termites. So if it kills termites, it definitely kills grad students, right? It's very toxic. It's very bad for you. It's a dark joke, but, and it's a gas, right? It's a toxic, odorless gas. It's not where you want to really be working. And so this makes it challenging for non-experts in particular to make these type of sulfur-6 compounds to do proteomics and covalent protein modification. So Emily Stacy, another graduate student in our lab, was able to actually show that the sulfuryl fluoride can bind in a very similar way to the same MOF I already showed you, with very high capacity. And what that enables you to do is fluorosulfurylation of many different types of nucleophiles. So every substrate in the scope I'm going to show you is a bioactive molecule, either a biomolecule or a drug. So we can do many different phenols here. This is one cool one, I think, pseudo-capsaicin. That's an analog of the molecule responsible for the taste of spiciness. I'm pretty sure that when you do this to it, you take away all the spiciness, but we never checked. We should not check, at least not by eating it. But you could do many other, again, nitrogen heterocycle molecules here. Then a great example of how exquisitely selective this is. If you look at that molecule, lots of different nitrogens and oxygens, and it goes just after the heterocycle here. But because sulfuryl fluoride binds incredibly strongly to the MOF, it actually is so stable that we can leave this gas-loaded MOF laying around on the bench, and it doesn't lose the gas too quickly. So one last thing I want to show you with these gas-releasing MOFs, I'm just keeping an eye on the time here, is that we can use them in not just transition metal and thermal chemistry, but also electrochemistry and photochemistry. I'm just going to go through this quickly because there's one more story I want to show you just to wrap up and try to keep us on schedule. But in long story short, what John Chen was really interested in doing was taking advantage of the power of photochemistry combined with these fluorinated gases and being able to do all kinds of different diversifications. Photoreactive catalysis has completely changed organic chemistry. So we wanted to be able to do it with these fluorinated gases too, to develop sustainable ways to make things with light as the primary energy input. But our MOF, as designed, is terrible for photochemistry. Because it absorbs visible light, it's yellow, it's very strongly colored, it is not compatible with photochemistry at all. It inhibits it, as I'll show you in a second. So John Chen went back to the drawing board and found another MOF, which is based on aluminum, and this simple organic molecule, and many of you have probably learned about, for example, how conjugation leads to strong light absorption. This molecule is much less conjugated, so it doesn't absorb visible light. We have aluminum, there's no unpaired electrons. This is a very compatible MOF with every type of photochemistry and also electrochemistry. And what John Chen showed was that this MOF was much more compatible with photochemistry than any other type of porous material, including zeolites or the MOF that we developed previously. And the MOF also still is able to bind gases really strongly, even though it doesn't have those coordinatively unsaturated metal sites, those really loose acidic sites, because it binds them through many different weak CH bond or hydrogen bonding interactions. And so I'll just summarize all of John Chen's beautiful work just by saying that this enabled us to develop many different types of photochemical transformations of fluorinated gases, You can just see the diversity of transformations you're able to develop here. And you can imagine how much work it was to figure out what I am showing you right now, but I'm just going to skip through it all and say, wow, Jiachen did a lot to show that this could be useful and develop these new, interesting, really difficult photochemical reactions. And so we also wanted to think about other ways that we can activate fluorinated molecules and use them in organic synthesis. And so something our lab has been interested in, many others, kind of a hot new topic in organic chemistry, is using electrochemistry, even though electrochemistry is actually one of the oldest types of chemistry out there. Organic chemists only figured out it existed like 10 years ago. And so that's not fully true. There were people working on it, but it exploded about 10 years ago now. And so we were interested in seeing if we could use electrochemistry. That joke was for John. He's chuckling back there. He's a real electrochemist. So if we can actually take an electron and transfer it to these types of halogenated molecules, you can undergo a process called mesolytic cleavage, which is essentially similar to homolysis of a bond, but where the two species you generate have different charges. So for example, here, this radical anion can fragment into a negatively charged anion and a neutral radical. That's the mesolytic cleavage. And of course, we already saw that if you can make radicals, you can do basically anything. You can add them to alkenes, you can do other types of functionalization. And so Yihuan was able to show that many of these simple fluoroalkyl gases are actually redox active. They can be electrochemically reduced. That's what these show you, this what are called cyclical tamograms. So you go more negative with potential. And when you see current start to flow, it means something happened. In this case, it's reduction and then radical generation. So using this, Yihuan was able to develop this radical trifluoromethyl reaction of alkenes, where we can generate trifluoromethyl radicals from this partner. It adds to the alkene on the end. That's what radicals love to do, generating a new radical, which we can trap and make borylated compounds here. And so this again works with a relatively broad scope of partners here. We can do many different types of alkenes. This is a common theme when you're demonstrating the utility of an organic chemistry method, right? You want to show it works on many different types of molecules, including drug molecules as well. I hope that Yihuan did not eat any of these. Usually you should not eat borylated things anyways. But it is, again, very general. We can do many different types of fluorinated functional groups here. So you can see these pentafluoroethyl, isopropyl, and propyl and butyl, many different types of fluorinated functional groups, all of which have slightly different biological properties. We can install all of them using this reaction. And with a little bit more work, we were even able to install this CF2H group. This is a unique functional group in drug design because it's actually a very strong hydrogen bond donor. This behaves like an alcohol, if you can believe it. Because those fluorines activate the CH so much, they make it so acidic, it's very similar to an alcohol. But again, we have many enzymes in our bodies that know what to do with alcohols. They don't know what to do with a CF2H group. So we can actually make these very nice using this. Okay, something kind of cool we're doing now is trying to interface this gas-releasing bomb strategy with robots to try to do even faster reaction development. So Danny in our lab built some robots. Like they're kind of loud when they're working, but they work okay, and we're able to actually do high throughput reaction development using those. But the last thing I want to do is try to deliver a little bit on the promise to you. The last thing I want to talk about, because I motivated all of this by saying fluorine is incredibly important in drug design. Hopefully I convinced you of that today. I also mentioned that fluorinated gases are greenhouse gases, but none of the gases I showed you today were really greenhouse gases of concern. None of them are on this plot. The only one of them that's really a greenhouse gas is sulfurofluoride. And the only place that cares about it is California, who's put restrictions on it. They use it a lot to kill termites, so they're worried about emissions of it. So sulfurofluoride is a potent greenhouse gas. We are able to capture it and use it. But what about these, what we call like the 10 most nefarious fluorinated gases? Can we use any of those to make drugs? And the one that I want to talk about today is this molecule called fluoroform here, CHF3. It's a molecule you probably have never heard of before. It doesn't come up very much in organic chemistry, but it's actually really, really interesting. Well, it's actually pretty useless. That's probably why you've never heard about it. But where it comes from is interesting. So this is actually a pretty simple SN2 type reaction that we do here. We take chloroform and fluoride and we mix them together and we get, sequential replacement of the chlorines with fluorines just by SN2 chemistry. So if you get one fluorination, that's underfluorinated, you send it back to the reactor. If you get two fluorines, that's actually what you want because you can take this molecule and make tetrafluoroethylene, which is the precursor of the monomer to make polytetrafluoroethylene, PTFE, or Teflon, which is made on a massive industrial scale. But what happens if you get overfluorination, you get three, is they go, whoops, oh well, and just emit it to the atmosphere. And that molecule right here, fluoroform, has a 100-year global warming potential equivalent to 15,000 molecules of CO2. Its lifetime is a lot longer than any of us will be alive, incredibly long lifetime. Its emissions are growing, and it's not going anywhere because unlike many other types of fluorinated gases that are being phased out as refrigerants, we're never going to stop. We don't have a replacement for Teflon. We're never going to stop making Teflon, at least not for the near future. So fluoroform's not going away. But on the positive side, fluoroform seems like the natural molecule to install CF3 groups into molecules. And these are just a couple of examples of blockbuster drugs that contain CF3 groups. So our dream was, can we capture fluoroform and turn it into drugs? This is actually a collaboration with the pharmaceutical company Pfizer. And we really thought it could lay a template for how we might actually be able to do this. And so, long story short, we started off on this journey before we were working with Pfizer. Ron, a graduate student in our lab, found that certain zirconium-based MOFs bind fluoroform okay. But once we started looking into it, what we saw was the key to bind fluoroform is very similar to what I mentioned before for those aluminum MOFs that John Chen developed. Those many synergistic weak hydrogen bonding interactions, not those open metal sites. We want to go for hydrogen bonding. And so day one, a postdoc in our lab looked at this and tested many different MOFs for their ability to bind fluoroform, and found that actually there is one MOF that outperforms that open metal site MOF that I showed you previously, this magnesium-based MOF right here. That's the red plot, and here's the blue one. And what we're looking at is a plot of pressure versus uptake. So the steeper uptake you see at low pressures means that the gas binds more strongly to the material. So MIL 160, I'll show you the structure in a second. It shows unprecedentedly strong binding of fluoroform, incredibly high uptake at very low pressures, also with a very high final uptake capacity as well. And it's actually really cool how it binds fluoroform. If this is the structure of the MOF, it's a little bit hard to describe. This is just a truncated piece of it. But what it has is essentially lots of oxygens. So that the ligand is this furan here with two carboxylates, the aluminum hydroxides. There's oxygens everywhere. They actually form this ring that looks almost like a crown ether if you've seen those before. And so fluoroform comes in with that CH and it binds right into that little pocket there. It binds really strongly without the need for any open sites. Okay, and what's nice is that the MOF works better for doing trifluoromethylation chemistry than using a balloon of fluoroform gas does. It's more reliable and it gives higher yields in this nucleophilic trifluoromethylation reaction here. So Daewon was able to show that that works for a reasonable scope of molecules, including a couple of drug and bioactive molecules. It enables many other types of nucleophilic trifluoromethylation reactions with many different types of electrophiles. That's a typo, it should be electrophiles. And also metal catalyzed or mediated reactions here with copper or silver, where we can do trifluoromethylation of boronic acids, alcohols, phenols, thiophenols, and aryl iodides as well. So I think this is starting to get us on the path where we can design a MOF that can bind trace fluoroform from an emission stream and turn it into a drug molecule in one shot. So we now have to do this for every type of fluorinated gas and see if we can really make that dream into a reality. So that's where I'll end. I've been trying to say the names of everybody who did this work throughout, but I have to thank all of them, of course, and the funding agencies, all of you for coming out on a Saturday afternoon, and I'd be happy to take any questions you have. So thank you.
Any questions for Dr. Milner?
Yeah, go ahead. Yeah.
Thank you for this wonderful presentation. I'm kind of wondering about, so we're trapping greenhouse gases with these MOFs, ideally.
Yes.
How does that actually work? Are you just like taking your MOFs and throwing them out to the air, or what does that
Yeah.
look like?
So what does it look like? That's a great question. And I'll try to give a bridged answer. So you can think about doing direct air capture. That's what that's called, where you can remove it. We've designed MOFs that can do that for carbon dioxide. You can open them to air and they will pull the CO2 out of the air. That is an approach that people are doing with MOFs. So that's usually called direct air capture or capture from what we would call a diffuse source, the CO2 all around us. It's hard to do with most fluorinated gases because their concentration in the atmosphere is like parts per trillion or lower. So they're so dilute that it's hard to grab them. So sometimes a better approach is to capture them where they come out, which is we call point source capture. The point, you could point to the source, chloroform is coming from that Teflon factory over there, right? Not literally over there. I don't know, you know what's over there, but you know what I mean? So what you would do is you would imagine you've got the smokestack in every factory or power plant, right? And the gases that are coming out of there, you put a column into it. It's basically like running a flash column that's MOF, and the gases go through and it just grabs the bad ones and lets something innocent like nitrogen, water, whatever go through. So that's how you do point source capture. And that has been really well developed for carbon dioxide on both sides, but not really for other types of environmentally hazardous gases. Actually, there's one other one, which is SO2. We used to have this really bad problem with acid rain. It actually killed a lot of lakes in the Adirondacks. Some of you may have learned about it in school. The way we got around it is we scrubbed SO2 out of the emissions, sulfur dioxide, out of the emissions of coal power plants. So that's done with usually like calcium oxide or something like that. So anyways, you could imagine grabbing it out of air. I think that's viable for something like CO2. But for many of these more dilute gases, you want to go to those point sources and stop them before they're ever released into air. And when you actually do the separation, it looks like running a column. You pack a column with the MOF and you flow the mixture of gases, and they take different amounts of time to travel through the column, so they come out in different times. So it's really like doing flash chromatography.
I've got one.
Yeah.
So I think in one of the earlier stories you were telling, you were talking about this kind of screen that a student named Mary did, checking for all the through all the different MOFs to check for VDF binding.
Yes.
Is there a high throughput way of doing that, or was that kind of a manual?
Oh, I wish. Yeah, no, it's actually very low throughput way to do it. We've gotten some higher throughput ways. So for example, that's what Jia Chen was trying to develop with the balloon thing. It actually works relatively well. It sounds really dumb, but you can take them off of known mass and a balloon of a known gas, and you expose it. It will pull some of the gas, and you just take the solid and weigh it, and you can calculate the uptake. It's a little, that's the best way we have to do high throughput. But what Mary showed there, what that was determined from was actually 3 separate measurements using a specialized instrument we have in our lab. And for each sample, she had to do 3 measurements. So it's actually a lot of work to do it in that way. So I think it's a great opportunity if anybody's interested in robotics or high throughput experimentation. Gas absorption is usually very slow. So if you want to try to identify a good material for capturing carbon dioxide from air, it could take months to just collect the data to really precisely know how strongly and how much CO2 it binds.
If there's no more questions, let's thank Dr. Miller one more time.